So I'm going to be doing a simplified model of this problem. This is a single cylinder, perhaps in an IC engine where there are multiple cylinders, but we're only concerned with one of them. And it is a problem that we will be doing probably in a week or so, exactly like it is. However, today I'm going to be simplifying this problem. Notice that in a setup like this, you have a crank. There's your crank. There's a crank. There is the connecting rod. Here is the piston. And this is the path that the piston takes in the IC engine. Our simplified model looks like this. So we have a piston. The piston is represented by this block. We have a connecting rod right there. And we have a crank. There is the crank. And this is the path that the piston takes in the connecting rod. Okay? I'm sorry, not in the connecting rod. In the engine. Okay? Good. First, we're going to create a cartoon. Then I'm going to come and create a mechanism out of this thing that we created. It's, you know, and make a cartoon out of it. That's really what I meant. Okay. And finally, we're going to come and put some physics into the problem. For example, I specified the speed of the rotation of the crank. And then I say, hey, what is the acceleration of the piston, for example? What is the acceleration of the connecting rod, etc. Why we need these accelerations? Because to do stress analysis on these pieces, you need the acceleration of the individual parts. Okay. All right. Now, I have taken some dimensions here just for the sake of illustration. They don't have to be like that. Obviously, if these are different, if the crank radius is different and the connecting rod is different as far as the size goes, then the accelerations will be different. However, this size has nothing to do, the size of this block has nothing to do with the acceleration, okay? Or the size of the track has nothing to do with the acceleration. Okay. One other thing today, my first approach is going to be use the magic wand to create the joints out of the restraints that I put in the assembly design. Okay? And once I do this problem and you see everything, then I'm going to come back and show you if you wanted to create these joints manually, how would we do that? I may or may not be able to finish that thing depending on how things go. Okay, are there any questions? All right. So we're going to create a product file first, a new product, say OK. Notice that I'm not in assembly design. To make our job easier, I'm going to switch to assembly design so that you don't get intimidated with these icons here. You shouldn't after two lectures. Okay, now, immediately I'm going to save this thing. File, save management, save as, desktop, just so that I don't have to scroll through all my stuff here. I will make a new folder, but the name of that folder, I'm going to put a 1 so that it's way on the top. And that is going to be, this is lab 51, and it's July 9. July 9. And it's going to go in there. Good. So I'm going to insert my first part, which is going to be that track. I'll make that track first. New part in there. And I'm going to right-click, Properties, Track, and Track. Please note that these parts or any of the stuff that I do here, there's not a unique way of doing it. You might decide to do this thing differently as far as the creation of the part is concerned. So I'm going to make the track, and on that vertical plane, I will sketch a 1 by 1 square because I'm going to pattern by 10 inches. So there is a 1 something like that. Let's make it 1 by 1. Again, these sizes have nothing to do with the actual mechanism and at least the size of this track. And then I'm going to pad it by, I think I have 10 inches. Okay. So there is going to be my track. You know what? I'll make this thing a little bit longer. I'll make it 15. It has nothing to do with these dimensions. Okay. Now, I want to make a pin here, okay? The pin being this thing, okay? Now, you don't have to make the pin. You can actually make a hole because you want to create a revolute joint here. All you need is the axis of a hole with an axis of a hole or 2 edges and 2 faces. You want to make a pin? Fine. You don't want to make a pin? You want to make a hole? Fine. Try to make the stuff that we do it as the problem is given to you. And the reason is, if this problem was given to you on the test, and you made something that is dramatically different from what we gave you, and of course it didn't work, okay, if it works, I have no problem. Okay? I have no problem. But if it didn't work, at least give us the opportunity to give you some part marks to make a hole or a pin or something like that, okay? If your part is completely different and it doesn't work, then how do we give you part marks? Okay, so on this face, I will draw a circle. The actual location of it, it doesn't matter, but I will make the diameter of it, just like the problem says, 0.5. Okay, so diameter 0.5, exit, and then pad it by also 0.5. Very good. This is it. Save it, and you know how to save it. You go all the way to the top. You click on the floppy, and it'll save it for you. Now let's insert, the next thing is the connecting, let's do the crank. So insert, new part. Say no, this is going to be my crank. Right click properties. Crank. And the crank. Okay, let's go make it. Okay, that's good. Of all the 50 people who are supposed to be in this class, all 12 of you are present. Excellent. So we make it. So on a convenient plane, what is my, okay, on a plane, and on purpose, I'm going to make these things out of whack. So on this plane, I will sketch. Yeah. Okay. So something like that. Okay. The dimension of this from the center of this to center of that is 6.5. Okay. And these radii I put down, I don't know, the outer one I put 0.7, diameter 0.7. And I already told you why we want you to do this thing the way it's given to you. In case things don't work out, at least you can collect some marks for the something that you made, assembly that you made, 0.7. Okay, good. Now there's going to be a hole in here and a hole in there on the other side. And I'm asking you these radii or these diameters to be 0.5. Yeah, 0.5. Oh, I just realized something. Oh, yeah, that's a crank. Sorry, not 0.5. Actually, I looked at all the wrong numbers here. This one is 3.5. I'll fix these. Okay, 3.5. was looking at the dimensions of the connecting rod when I made that. Okay, and this thing is 0.5, and that is 0.5. 0.5. Excellent. Exit, and padded by 0.25. Now notice that I could have created these things as I go along. In other words, in the right spot, I could have created them. Except that if there are no assembly constraints, then you're going to have to put it on it later on. Now notice that this diameter, this looks to be too big. Let me see. This is radius 0.5. I want diameter 0.5. That's why it looked too big. Oh, no. What I mean is, okay, diameter 0.5. That's what I want, 0.5. I probably have to fix that outer one also. Yeah. Undo. Let me see for a second. It says this diameter is 0.5, this diameter is 0.5. Obviously, that's wrong. Okay, so maybe this is 0.7 and this is 0.5. Okay, good. One of the dimension is wrong. That's okay. So this one, this diameter is 0.7. And this radius, where is that? This one, I didn't even put a radius here. I have to do that. This radius is 0.5. Diameter of 1. Oh, gee. Oh. Wait a minute. What is that? Diameter 0.5. This should be diameter 0.5. Good. And this obviously is 0.7. This radius, or let me make this in diameter, 0.7. Okay. And that radius, this radius, or that diameter is 0.5. Oh, we spent so much time on this. But I hope you understand my point. If your mechanism did not work at the end, whatever you did, and if these are wrong completely, then we have no basis to help you. Okay, exit. I'm going to pad this thing by, yep, that's fine. This is correct. Very good. Save it. Go all the way to the top. All the way to the top. Save it. Something that should have taken me maybe a minute to do took 4 or 5 minutes, 4 minutes. Insert. Insert. New part. In there. Say no. Always say no. Sometimes read it. Properties. If you have never read that thing, you should. This one is going to be the connecting rod. How about the con rod? Con rod. Or sometimes people call it coupler. Okay. Con rod. At the rate that you're going, I don't know, you may not be able to do the latter part of this. Double click on it. Okay. So the connecting rod looks like this, and there are different ways of doing it. For example, you can draw that and then go make a hole here or a pocket here and make a pad there. You can do a multi-pad. So let me, to save time, let me draw this thing and make a hole there and make a pad there, okay? Because you can do this whole thing with a multi-pad instead, in one shot. So double click on it on purpose on this plane. I will sketch on purpose, okay? So let me make a thing that looks like that connecting rod. We'll fix the dimensions in a second, like that. Okay. This is 6.5. The length here is 6.5. And when I say the length means from that center to that center. These other dimensions have no bearing on the problem. 6.5, that is the one that counts. Okay, let's put some, to make a hole automatically here, let me draw a circle. We're going to put the dimensions. Dimension of that hole, the diameter of it was 1. Okay, and this guy, I want it to be, I'll make it 0.7. There's a typo in the description of the problem. So let me make the diameter points. It should be bigger, right? How about making it 1 point? I don't know, to see how it looks like. Okay, no problem. We're going to fix it. Fix it. So that's sent that circle. Control that circle. We want them to be concentric. There. Did it. Okay, since I want it to look exactly like what I gave you, I'll make this diameter 1.2. Radius 0.6. How about that? Excellent. Yeah. Exit. Why am I having a problem with sizes here? So let me see. Let me see for a second. This guy, it's not a good day. What is this? This is radius 0.25. Okay, so let me go here. Diameter, that should be 0.5. Okay, and I'll make this thing smaller. So 0.6, 0.7, 0.7. That's better. 0.7, 0.7. Diameter 0.7. Not a good day. What? Diameter 0.7. There. Mark marks. Good. Exit. We exit. We now pad it by 0.25. 0.25. Say okay. Now on that face, I will sketch a little circle, which is concentric with this guy, which we can do that in a second. Okay, so first of all, I want this to be concentric with that. So that guy control this circle. We want him to be concentric. Very good. And that size of it to be 0.5, diameter to be 0.5. I think this one is right. Yeah, that's good. Exit. Pad it to make that pin. And the size of that pad is 0.35. Now, please remember that instead of making a pin here, if you made a hole and you made your revolute joint based on the hole, perfectly, no problem. Okay, as long as you did the problem, it worked all the way to the end, and you got the stuff that we want, no problem. But if that didn't work, and you made your own things, that's problematic. Okay, so go here, save it, and the final thing is the piston or the block. Okay, so insert a new part, the block. properties. This is the instance name. Notice that I insist on using the correct instance name because that helps you make sure that the joints are correct or not later on. And there's the block. You double click on the block. So on a convenient plane, on purpose, I'll make it this XY plane. I will draw a 1 by 1 square. One by one. Exit. Hey, you know what? Now that we are here, what does I show you the multipath? Okay, I'll draw a circle there. That is going to be making that guy. Okay, so diameter 0.5, length 0.75. So let's go ahead and do this. 0.5, 0.75. Okay, so let's go here. First of all, I want this thing to be centered. You know how to do that, right? How about actually doing it like this? This point, control that point, control the center here, make it equidistant probably. Yep, it puts it right. Okay, very good. Okay, so let's put dimensions. This is 0.5, diameter 0.5. Excellent. Exit. Now, if I do a pad, there's going to be a hole here. I don't want a hole. I want a pin. So I'll do a multi-pad. Okay, so this one is the what is that? This guy is the square. So I'll make that thing 1. 1. Oops, 1. And this guy is that little circle in the middle. So that I'll make it 1.75. 1.75. Do it any way you want, okay? We don't care. So, let's go here, save it. Oh, no, go all the way to the top. I didn't go all the way to the, this is selected, but I'm not there, see? I'm still in part design. Double click on it so that you go in the assembly design and then you click on the floppy. Okay. Move this thing out of the way. Let's minimize these things. Collapse the tree. And now we're going to do the constraints. First thing, fix the thing that you think is reasonable. That is the piston path or the track. And I tell you why, because I don't want this thing to move with respect to this XYZ. Okay? I anchored this. Now let's insert the crank in there. So coincidence between that axis and this axis. Notice that even if this was a hole, it would work. Even if it was a line, it would work. So this will be rotating about that edge. That's ridiculous. But you can do it. As a mechanism, it doesn't matter. So coincidence between this face and I want to rotate this thing and take the back face, but I'm too lazy to do it. So I select this. Notice these arrows will pop up. You flip it and update because I was too lazy to rotate. Now I want this thing to go up, and you know how you do that is you go to the move. Some people do it with the compass. I don't like to use the compass. I use the manipulate. So I'm going to rotate about this axis. Did I select it? This axis? I like this thing better. Good. Now let's put the coupler in there. So coincidence between this axis and that axis. Notice that even if this was a hole, it would work. Okay. and coincidence between this plane and that plane. Now, if they don't fit together right, we flip those arrows, we find out. Yeah, let's say it didn't fit right. It works as a mechanism, but I don't like it. Double click on it, flip the arrows, one or the other, it doesn't matter, and update, it'll move out. Good. Okay. Now let's put this guy on this block on the track. So coincidence between, for example, this face and that face. And once again, if they don't fit together, you flip the arrows, okay? So we say, okay, update, we'll find out. You see, it didn't fit right, so double click, flip the arrows, say okay, update. Good, that's better. And coincidence between this edge and that edge. Remember, this is going to be a prismatic. It's going to go up and down that track. It is going to be a prismatic joint. Now, you want to put this hole on that pin. Now, you can do that. You can do that. There's no problem. And when you do, okay, when you do, well, first of all, you can create a revolute. Let me tell you something. You can create a revolute between this and that, but the faces don't match, and that's going to be a revolute offset. My point is that it doesn't have to be revolute. All you make sure is that this whole axis aligns with this whole axis. That's become a cylindrical. But as long as it works, it doesn't matter. So coincidence between this axis and that axis, and update. Okay, good. So when you do these problems, you might do it and it might work fine. And some of the joints that you have may be different from mine. Okay? For example, it could be because of issues like this, because it could be that the way I did it, I made this thing, because of my constraint, it became a revolute joint, yours became cylindrical. But as long as it's doing the task, it means that whatever you did or whatever I did was correct. Okay? Now, the other thing is that notice that when you do that, it looks like this guy, I don't know, this guy may be going through the part. It doesn't matter. You're doing mechanism. CATIA doesn't care. If that goes through that, it doesn't care because you're not interested in that aspect. Actually, I don't think it is. But if it is, then you go and change the multipath, this height. Let's go and do that, actually. It just looks more respectable. This was what? This was the Conrad, right? Let's go to the multipath. Oh, actually, I didn't do a multipath. I did a path. I didn't do a multipath here. That's okay. Just double click on it. Make it I don't know. Make it 0.25. See how it looks. Preview. Okay, so surface is flush. If it's bothering you, as a mechanism, it really doesn't matter. Okay, good. Let's go ahead all the way to the top. All the way to the top. Save. All right. Good. Now, how do you know whether, how do you collect part marks here? Well, if nothing else worked, what you can do, you can say, okay, you know what? I'm going to move these things randomly. Move this thing there. Move that guy here. Do a little bit of rotation. Rotation there. So the GA is going to say, okay, this guy couldn't finish the problem as it was stated, but at least the parts were created okay. But let me see if the constraints are okay. Update, they should go back where they are. Now, if you look at your homework, for example, the homework that I posted, and the solution is posted. Okay, they're all the same, by the way, you know that. You see, the way the homework is going to get marked, it says create an assembly and relevant constraints. Okay, so what the GA is going to do is, if this had 2 marks, 2 points, if you made the parts like we asked you, okay, you get half of it. But if your constraints were not right, in other words, you moved them apart, you updated it, and didn't go back where it was, you don't get the other one mark. Okay, now the other option of checking that is this, and this works in majority of cases. You're going to say, okay, let's do this move again. Remember how I moved them apart? Check this box. In other words, hold the constraints in place. Hold the constraints in place. Check this box. And let's rotate the crank about this axis. So here is arbitrary rotation about this axis. There. Did you take it? No, no. Not this. Cancel that. Let me try again. Check this box. This is very important. Arbitrary rotation about this axis. Okay, look. Grab the crank and move it. If your constraints were not okay, this would not happen. This is an indication that your constraints are holding up. Okay? Good. All right, so excellent. Now we're going to go to digital mockup, DMU kinematics. Okay, let me see. I have 15 customers. Are there any questions? Okay. Get the magic wand out. So this is the main toolbar, DMU kinematic. Get the magic wands out. Magic wand out. It says, well, would you like to create a mechanism? Yes. Would you like to call it mechanism 1? Yes. Would you like me to automatically, magically create the joints? Yes. Now, ideally, this will go to 0 out of 4, see unresolved pairs, 0 out of 4, but that doesn't always happen. In these simple problems, it does. It's not the end of the world. You have to go and fix it, find out what the issue is, and there may not be any issue. It's just that depending on the type of problem, type of joint that you're doing, that may not say unresolved pair 0 out of 4. Okay, good. Now let's check our joints. Gradually, through the next 3 weeks, you will get to know what the joints are before even you looked at them. Remember, I did axis and axis, plane and plane. This is going to be revolute. I did axis and axis, plane and plane. This is going to be revolute. Here, I did axis and axis. That's going to be cylindrical. And this is, of course, edge and edge and face and face. That's going to be prismatic. So there should be 2 revolutes, 1 prismatic and 1 cylindrical. Right here, 2 revolutes, 1 prismatic, 1 cylindrical. And notice that because you use the correct instance names, it tells you exactly what these joints are between. If you had not changed the name of the instance, it would not say block and the conrod. It would say part 1 and part 2, even though you changed the name of the part. Okay, now degree of freedom is 1. Obviously, you can make this thing angle-driven. You can make this thing angle-driven, or you can make this thing angle-driven, or you can make this thing angle-driven. That'll make this thing 0. However, because you're attaching this thing to a crank, obviously, this is the most reasonable one to change. Okay, this is going to go to the motor, and you just turn this thing, or electric motor, for example, if it has one. Anyway, so that between the track and the crank, make it angle driven, 0 to 360. Okay, mechanism can be simulated. Let's do that manually first. Remember, this is the manual one. You click on it. There's a single sliding bar. Let me call it. Okay. There's a single sliding bar. We already checked that in assembly design, but that was not mechanism. The mechanism was not created. That only showed the correct constraints. Now we have a mechanism, mechanism 1. Okay, good. Now let's create a cartoon. So you go to, where is that, simulation right there? You see this? Simulation. It's mechanism 1. Say okay. You get two dialog boxes, move this thing all the way to the end, insert, rewind, choose anything but one, and play it continuously. It's in the same direction. What did I do here? Okay, let's double click on this. I said cancel, I think. Okay. Continuous play. Go. No physics. No physics. Very good. That worked. Would you like to create a replay? Yes, I do, because I want the trace of something. Okay. Now, by the way, I want the trace of the middle point of this crank. Okay, I need a point there. Okay, so let's go to that crank first of all. I'm going to double click on this to go to part design right there. Right now, I'm in that crank. So let's create a point. I don't know, on that surface. I'll just take a random point, something like that. Okay, this is good. This blue one is fine. Whatever it is. I don't know, it's not exactly in the middle, but at some point there. Okay, back to the DMU. Okay. First of all, you compile that simulation. If you want to get a trace, you need to compile it. Well, let's generate a replay first. Good. I'll use one. Bad. That's no good. Let me delete that. Try it again. Compile. Said don't use one here. Okay, generate replay. Give it time. Okay. Now I want to get the trace. Read it carefully. The point. This is the point to be traced out. And the reference product, of course, is just that product one. 26 point, no problem. There we are. That point goes through this ellipse. Okay. Let's save this thing. File, save management, save as. Because in order to bring that into the model, you have to save it. Where is that? That's the first one, July 9. Trace is fine. Say OK. What? Following document will not be saved. Okay, no problem. That's fine. Okay. You can screen capture this and send it to the GA, because that's one of the things that we want in the homework. It says here, create the plot. No, wait a minute. Create the trace of a point D. Okay. Note that in order to create the trace, you must first create a simulation and then compile it. Okay, fine. To create a replay. So if this was a homework problem or a test, what would you do? You say print screen, start the Word file, paste it, save it, file, save as, browse, desktop, my first folder. I'll call it my trace. My trace. Okay. My trace. Save. Okay, good. Close it. Now, if you want to bring this thing into a mechanism, just close that, say File, Insert, an existing component. In there, go get that trace, desktop, first folder, right there. The trace, not that one. Where's the trace? Right there. Bring it in. Excellent. That's this point, right? You replay, play it continuously. You see, continuously. You see that in one direction. That point is going to go through this. Now, you know what's going to happen? Before the homework is due for you guys, it's going to be a long time. Oh, actually, yeah, for you guys, it's going to be in about. This homework is due for you folks a week, no, 24 hours after next Friday. Okay. Okay, so you got it today. This homework is due. No. 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 Yes. Wait a minute. When is this thing due? We gave it to you on Wednesday. Yeah, it's 24 hours after next Friday. So it's going to be next Saturday, I'm sure. Okay. Now, here's what I'm going to say. People are going to email me. Should I submit a three Word document, one Word document? Where is your template? How do I do the template? What happened to PDF? All I'm going to say is go watch the lecture. Okay? Good. Now, let's create a video file. So one more compile. This time I don't want a replay. I already created a replay here. Animation. The name of it. Let's go to that folder. My third video. Don't use one. Say okay. Good. So let's go check it out. Where is your folder? Section 1. It wasn't this. I started with, the name started with 1. Okay, right here. That's the one. My third video. There we are. Okay, good, good. Now we're going to go put some physics into the problem. Are there any questions? Okay. So, first of all, save everything. Anything that you don't like, you want to hide, go ahead and do that. For example, the trace I want to hide right there, gone. Now, to put physics in the problem, we are telling you what the speed of the rotation of this crank is, 60 RPM or one cycle per second or 360 degrees per second. Okay, so we're going to go to, first of all, f of x. Where's the f of x? Right there. You click on the mechanism. There's only two things you're going to get: time and okay, where is that? Cancel, cancel, cancel. F of x. There. Two things. The time. See, I have to click on this mechanism one. And angle. Angle equal to, add a formula. Angle equal to 360 DEG divided by 1S times time. There's your time. Constant speed, right? There. So there is the physics of the problem. It didn't complain because the units are matching on both sides. There's no inhomogeneity, etc. And that is reflected in the tree right there. In your mechanism, the law line is filled, and it's that formula that you type. Okay, good. Now, I want some information about this point. For example, I want the speed. Let's say acceleration. Acceleration, magnitude of the acceleration. That's what CATIA calls linear acceleration. If it was the x component, you'll say x acceleration, x acceleration, or y acceleration, or etc. I want, well, actually it says x linear acceleration, y linear acceleration. If you want the magnitude, just linear acceleration. So first thing that you're going to do is you're going to go and create a sensor. Sensor is, for the name of it is fine. This is fine. The reference product is that track, and the point is this point. What is that? This point. This point. Now, let's say I also wanted information about some other point. For example, this is fine. This is fine. No problem. I'll do another one. Another one, you'll see why. The reference product is still this. The point is that point. So basically, I'm asking for information to be generated for this point, which is point 1, and this point, which is some vertex, vertex 1 or whatever. It's going to be called vertex 1. Notice I have two sensors here. One of them is for that. The other one is for this. Okay, good. Now we're going to go to simulation with laws. First of all, how many seconds? Let's do one complete, two cycles. How about that? So that's going to be 2 seconds. Because otherwise, do it for 10 cycles. Two seconds. Activate sensor. Now notice that what happened, this is a long list for both the point 1 and the vertex 1. See that? This is for the first point. 1, 1, 1, 1, 1, 1, 1, 1, all the way down. And then in the rest of the table, you have 2, 2, 2, 2, 2, 2, 2, 2. So let's say that I want the acceleration of the point, not the x component, not this one. Magnitude is here. Where's the acceleration? Ooh, not that. Angle, right here. See that? This is point 1, first one. Linear acceleration, not the component. We're asking for it. And I want for that vertex point. We go down here. Go down, 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 down for point 2. Linear acceleration of point 2. So I'm going to get 2 graphs on the same axis. One for the magnitude of acceleration of the point on the connecting rod, one for the vertex. Move this thing out of the way. Play it. 2 cycles. Stops. And graph it. The top one, the yellow one, is for, let's read this carefully, for point 1, this is on the connecting rod. This is for point 2, which is that vertex of the vertex of the cube. And if we ask for this, or if we ask for one of them, print the screen. You know what? If people come back to me on the test, on the homework, and say, well, why did I lose marks here? You're being told what to do. Word, paste, save as, desktop, right folder, way on the top, and this is going to be acceleration versus time. Now, you should give us exactly the thing that we want. If we did not ask for the acceleration of that vertex of the cube, don't give it to us, please. Okay? There's going to be one graph on this if we just ask for one point, and that's the point, whatever it is, on the connecting rod. Good. Now, you don't need this anymore. Last thing. Suppose I want to create the plot of acceleration of the point D being this point, versus the acceleration of that. Okay, no problem. I already have requested all the information that I wanted to, but I'm going to say options, customize plot, add. Let's go get it. So this was acceleration of point 1, right there, versus acceleration of point 2. Oh, this is point 2 linear. Oh, this is what was it? Accelerate. I can't remember. What did I pick? Cancel. Okay. Let me, for this, I want, it's kind of hard. Oh, you scroll down, you can see it. So acceleration, linear acceleration of right there, point 2. That's what I wanted. Okay. I'm sure this is okay. Yeah. This one is linear speed, right? That's not what I want. This one, I wanted acceleration. This one was 0.1, not speed. There. They're both acceleration. Say okay. And close. Let's do a graph here. There we are. There we are. Because I had already generated requested that information generated. So the graph of acceleration of 0.2, that's on the vertex, versus acceleration of the point on the connecting rod is a horrible function. That's what it is. Worry about it. You can try it, ask me, but I'm not going to do the second point. We have already gone through this thing for 50 minutes now. Are there any questions? So my plan is to stop the recording here, kill the session, start another session which says your remaining 2 hours, and the GAs are going to be here. I'm going to be here for only a part of the time because I have a lecture in an hour, so I'm going to go disappear. And then, of course, I have office hours during the day today. Folks, I'm going to kill this and then make another session in case you're interested.